single source shortest path using Dijkstra. It takes order e log v time when we are trying to do it using what priority queues or min heap, if you will. And then we saw that if you have negative weights, then Dijkstra just flops. And we saw actually an example where it fails. And then we saw another algorithm. Can everyone hear me all right?
Yes, Professor.
Awesome. Cool. And we saw that if we have negative weights, then we can use another algorithm called Bellman-Ford, which copes for negative weight by doing a lot more edge relaxations than what Dijkstra does. Dijkstra kind of relaxes every edge only once. And it relies on the fact that it can, if the weights are non-negative, then it can relax them in a particular order, which helps it find the shortest path from source to every vertex in the graph. Bellman-Ford does not rely on the order of the, well, it does not rely on the order of the edges that we relax. It says that I'm going to relax all the edges, but I'm going to do it v minus 1 times. And we saw that v minus 1 appears there because the maximum length of a path in terms of number of edges and not the weights on the edges is v minus n on a graph on v vertices. When we went from Dijkstra to Bellman-Ford, we kind of crossed an invisible boundary from greedy algorithms to something called dynamic programming, which we are going to study today. Okay, so dynamic programming was proposed by Bellman guy, this Bellman-Ford guy, and how do I go to the next slide? Like this. Okay, so dynamic programming. So the thing is, there is nothing dynamic about dynamic programming, and there isn't as such programming involved. Programming, particularly, programming as such means planning in the context of dynamic programming. The name was chosen just to get funds from military. They didn't kind of want to fund generic research. So dynamic programming was kind of a catchy name for whatever we are going to discuss. So what is dynamic programming? Well, it's on the face of it, it's pretty much what we saw as the divide and conquer. Oh, by the way, anyone can ask me a question, okay? So you can stop me, and the other way to ask questions is to add questions in the chat, and one of the TAs would stop me and ask those questions for you. All right, so dynamic programming is, on the face of it, pretty much the divide and conquer that we studied earlier, with the one distinction, which is right on here, solving each problem only once. Well, you would say that sounds like a simple thing to do, right? Why would anyone want to solve a subproblem more than once? Funny that you asked this question, or I do it on your behalf. The thing is, here's an example of a case where you actually solve a subproblem more than once. Let me try to notes. Okay, so I hope you guys remember Fibonacci numbers, which probably is one of the exercises that you do in the programming courses, I guess. So they start with 0, and then you get 1. And after that, what you do is you sum up the previous two numbers. So 0 plus 1, you would get 2, and then you will get 1 plus 2, which is 3. 2 plus 3 will give you 5. 3 plus 5 would give you 8. 5 plus 8 is 13. I guess at this point I should stop, but I'm having too much fun. So I'm going to go with 21 and 34. Okay, I should stop before I make a mistake, right? All right, so this is the 0 is the first Fibonacci number. So let me just put a bar here. 1 is the second one. 2 is the third one. 3 is the fourth one. and 5 is the 5th one, and 8 is the 6th one, and so on. Okay, so the problem again is to find nth Fibonacci number. I give you a number and I ask you, give me, for example, if I give you a number 8, I ask you what is the 8th Fibonacci number, and you report that this is 21. And the way we do it in programming classes is that we say that if this number is less than or equal to 1, then you just return this number, right? If it's 1, oh, hold on a second. Okay, थोड़ा सा messy हो गया. Let me just clean this up. Okay, so we say that if n is equal to 0, then I'm gonna return, sorry. If n is 0, you are asking me for the 0th Fibonacci number, then you should not ask me for 0th Fibonacci numbers. You should ask me the first Fibonacci number. I'm gonna return 1. I should return 0. Sorry for the confusion. Okay, the first Fibonacci number is 0. If you ask me for the second Fibonacci number, I'm gonna return 1. Finally, okay. After that, what I'm gonna do is I'm gonna just use the formula. I'm gonna return Fibonacci of n minus 1 plus Fibonacci, and Fibonacci is now f, Fibonacci of n minus 2. And that will do it for me, right? So pretty much what I define Fibonacci number as, right? So the first Fibonacci number is 0, second one is 1, and every other Fibonacci number is the sum of the last two Fibonacci numbers. Cool. Question is, what's the time complexity of this algorithm? Well, to compute Fibonacci of n, what you do is you have to compute Fibonacci of n minus 1 and Fibonacci of n minus 2. And that's pretty much all you have to do, right? There's nothing else going on in the algorithm. To compute Fibonacci of n minus 2, you have to compute fib of n minus 2 and fib of n minus 3. And fib of n minus 2 is fib of n minus 3 and fib of n minus 4. And fib of n minus 2 is whatever, okay? So I guess you see what I was going for, right? I am computing fib of 2 multiple times here. I'm computing fib of 3 multiple times here. And if you continue this tree, you will see a lot of overlap. You are solving the same problems multiple times when you're doing it like this recursively. Turns out this the time complexity of this algorithm is big of 2 raised to power n, or exponential. To be, I don't know, more nitpick, this is 1.51 or something like this to the power n, but exponential in any case, right? Which is not good. And the reason this is exponential is because there are sub-problems which are being solved multiple times. Sub-problems. And that's the problem that dynamic programming will solve us for you. Solve for us. All right, so dynamic programming is okay. Still getting used to it. Making sure that you solve each problem once by storing the solutions of these subproblems somewhere. All right, and it's related to divide and conquer, obviously, but it's also related to greedy, in the sense that whenever greedy fails, dynamic programming is something that gives you the correct answer. Let's see a few examples. So, two key conditions that are kind of a requirement for dynamic programming is one of them is the optimal substructure. This is a key condition for divide and conquer as well, right? You want to be able to solve a problem based on the solutions of the subproblems. If you can solve a problem based on solutions of subproblems, then you can apply divide and conquer. You can also apply dynamic programming. The second condition, which is unique to dynamic programming, is that you must have overlapping subproblems, which is in the sense that if you design a recursive algorithm like we did for the 5G. Hello, yeah. Cool. Okay, so second condition, which is unique to dynamic programming, is that you need to have overlapping subproblems, which means that in the recursive solution for the problem, you're most probably solving, you're always solving multiple subproblems. If that's not the case, then you can definitely apply divide and conquer. You don't need to apply DP in this case, okay? If there is no overlapping substructure. All right, it's the same example that we saw. This gives you exponential time algorithm. I mentioned that this is not, so it's big O of 2 raised to power n. So 2 raised to power n is upper bound in time complexity. But you can, but this is not the tight overlap. So what it means is that the exact time this algorithm takes is roughly order 1.51 something to the power n. All right, here is the dynamic programming based solution for this problem. What you do is you start with an array memo. The whole process is called memoization, not memorization. Memoization. You memo things, which means that once you have solved a subproblem, you keep its solution somewhere, so that the next time you have to solve the same problem, instead of doing the whole thing again, you just copy the solution from wherever you put it. So you're keeping your solutions in something called memo. You call the function fib memo, and then each time you are solving fib for a number n, you check whether that subproblem has already been solved. So so this is where we are making the check. We are checking whether memo of n is already set. If it's already set, then we have already solved this problem, and we will return that solution. If it's not, then we will go through the whole routine, which is that we check if n is less than equal to 1, then we return n. Okay, यहाँ पे थोड़ी सी fib की definition different है. Starting
Professor,
with
I think Mustafa का एक सवाल है. Mustafa, you can ask if you want to.
Professor, in the previous slide, could you please explain the first condition for DP again?
please switch the mic.
Mustafa, आपका mic बहुत can you try to?
Can you hear me now?
Yeah, I can hear you.
I was saying that could you please explain in the previous slide the first condition for DP?
The first condition for DP. So the first condition for DP is optimal. Man, that was like 3 or 4 slides ago. That's optimal substructure. What it means is that you should be able to design a recursive solution.
Could you come again?
So you should be able to design a recursive solution, which means that if you have a solution to some subproblems, based on those solutions, you can generate your solution to the original problem. For example, in the fib case, if you know the fib of n-1 and fib of n-2, then you can figure out fib of n. Optimal substructure was already in, for example, my third problem, right? If you have to sorted halves, then you can merge them to find the completely sorted list. Similarly, quick sort case, maybe we had the same thing.
Right, got it. Thanks.
Sure. All right. So I was saying that you can generate Yeah, so I was saying that यहाँ पे जो fib की definition है, this is starting with the 0th index fib. Okay, so 0th Fibonacci is 0, first Fibonacci is 1, and so on. मैंने जो अभी की थी वहाँ पे I started with the first index. Okay, so यहाँ पे जो solution है उसमें we are saying that if it's already set, so we'll use that solution. Otherwise, we'll do what we were doing in the recursive case, which is that we recursively find the n-1 Fibonacci and add it to the n-2th Fibonacci. Sum them up and send that back as the result. All right. So this is everything here is same recursive part. This first line is the magical part, which is that if you have the result already sorted somewhere, then you pull it. ये थोड़ा सा end के ऊपर भी हम कुछ कर रहे हैं. So before we return the result, we save it in our memo. We are doing the memoization. So that's also part of the dynamic program. The result of this is, let me try to do it here if I can. For example, if I'm doing fib of 5, so फिर मुझे fib of 5 करने के लिए, fib of 5 is, for example, not already in the memo, right? So this is, let's say, my memo, which is empty at this point. मैंने थोड़ी सी बड़ी बना दी है. So but fib of 5 के लिए आपको fib of 4 चाहिए. I'm just writing it f of 4 here. और फिर मुझे f of 3 चाहिए. f of 4 के लिए मुझे f of 3 चाहिए. But this time मेरे पास f of 3 पहले से होगा. तो I won't have to do f of 3 again. So f of 4 के लिए I only need f of 2. और f of 2 के लिए I need f of 1 and f of 0. So I would solve f of 0 and that would probably be 0 and f of 1 would be 1. उसके बाद f of 2 would be the sum of these two, which is 1. F of 3 would be f of 2 plus f of 1, which both of them are already computed, right? So I don't have to solve them. So I'm going to sum these up. I'm going to get 2. F of 4 के लिए मुझे f of 3 और f of 2 चाहिए, which is already solved. And f of 5 के लिए मुझे f of 4, f of 3 चाहिए, which is 5. Okay. So I had to sum them up, but the results were already there for most of the cases, right? So I only had to compute every Fibonacci only once, which means इस पूरे algorithm की time complexity has drastically dropped from exponential to linear. Are we good? Okay. Let's move on. Let's see a few examples.
Just one thing.
Yeah.
Is it linear in terms of the number of bits that are used to decode the number?
Oh, very good question. Very good question. I was really expecting this question. So it's linear. It's okay. It's not linear in the bits that we need to represent in n. Okay, it's not. So it was exponential in n, which is the number that you give, and we made it linear in that number. We did not make it linear as the size of the input. Very good question. Yeah, it's not linear in the number of bits. Any other questions? Cool.
Professor, I had a question that
Yeah.
Which tree are we following? Like if we did Fibonacci of 5, then Fibonacci of we need Fibonacci of 3 and 4 to find 5, and then further 2 and 1, and then 0. So like we are following the tree that goes from 4 to 3, 2 and 1, or like in the first nodes,
Yeah.
those who have height 1, the 3, Fibonacci of 3 and the Fibonacci of 4, like which tree are we following? The left half or the right?
Right. So when you are at Fibonacci of 5, you are making a call of f of 4. When f of 4 completes, then you make the call for f of 3. Okay. So f of 3 wali jo call hai, it's going to use already solved f of 3. So यहाँ पे जो call हो रही है, that's going to use the memo and f of 4 से जो f of 3 की कॉल हो रही है, that's actually gonna make the f of 3 call. So f of 4 से you will have an f of 3 and f of 2 call. अब f of 3 से जो call हो रही है f of 2 वाली, that's gonna be the original call. So can I make a, मैं next slide के ऊपर try करता हूँ. So I assume that's the question, but because so f of 5 say you are making a call which is f of 4. वहां से you are making a call which is f of 3. वहां से you are making a call which is f of 2. वहां से you are making a call which is f of 1. और यहाँ से there's a call for f of 0. Actually यहाँ से तो नहीं होगी. Is there an eraser somewhere here? I don't know. Okay. So f of 1 is, we know what f of n is, right? इसके लिए मुझे recursive call करने की जरूरत नहीं है. f of 2 से I will have to make f of 0 call. These are the calls that I am going to have to make. अब इसके अलावा जो calls हैं, can I change the color to blue? Okay. इसके अलावा जो calls हैं, ये calls f of 3 for example यहाँ पे होगा और यहाँ पे f of 2 होगा, यहाँ पे f of 1 होगा. They are using memo. Make sense?
Yes, Professor. Thank you.
Sure. All right, so there are two ways to do most of the time. There are
प्रोफेसर
क्या?
किसी ने स्लैक पर पूछा है कि अगर हम लाइक नंबर स्टोर करें तो वो स्पेस कॉम्प्लेक्सिटी भी तो बढ़ाता होगा, तो व्हाट अबाउट दैट?
Absolutely. Absolutely. And again, a very valid observation that while we are reducing the time complexity of our algorithm drastically, we are increasing the space complexity of our, well, increasing energy. So we do have to store solutions somewhere in a memo. Absolutely. Absolutely. We have an extra overhead on space. I agree with that. And that's the cost that you pay for the time complexity. Okay, good. There are two ways. Most of the time, there are two ways to do dynamic programming. One is the top-down, जो अभी हमने किया है, which is that you start from the problem that you're trying to solve, और उसके बाद फिर you figure out कहाँ पे आपको solution save करना है. Another way to do this is bottom-up, which is kind of more my favorite that I use in my research more, I guess. Which is that you start from the smallest possible problem और उसको solve करते हो और फिर ultimately you reach up to the problem that you are actually trying to solve. So Fibonacci के case में what you, I think मेरे ख्याल में है, instead of starting from n, you start from 0. Okay, so I'm looping, so इस case में ऐसा कोई recursive calls नहीं होती. You're not making any recursive calls. You start with a memo जिसके 0 के ऊपर you put a 0 and उसके 1 के ऊपर you put a 1 और उसके बाद then you loop from 2 to n, incrementally solving harder and harder or larger and larger subproblems, right? So that's kind of the bottom-up approach. Both cases may, it's just, I think, a matter of haste. Time complexity is going to be same. Space complexity is going to be same. The first one is recursive in nature. So at times, जो second वाला part है वो possible नहीं होता manage करना. तो you go for the first one और उसको करना थोड़ा मुश्किल हो जाता है. So we go for the first one. Otherwise, I like the second approach better, where you start with the smallest possible problems and you build your solutions for the next larger problem and so on. जैसे DP के case में हुआ. We'll see a couple of more examples. Okay, so the next example we are trying to solve has already been visited in this class at least a couple of times. Coin change problem. इसकी example पकड़ लेता हूँ. So here's an example. You have coins of 1, 2, and 5, and you want to make or want to pay someone 11 bucks using these coins, and you want to give them minimum number of bills or coins. इसका हमने greedy solution देखा था. We saw that the greedy solution works for all canonical coins, but अगर coins आपके canonical नहीं है, for example हमने ये देखा था कि if you have 75 rupees bill, तो फिर greedy will not help. The greedy approach was that you start with the largest possible bill or coin that you can pick, and then subtract it from, for example, N11, you will start with 5. You will remove 5 twice from N, so you will have 2 bills of 5, which means that you have already paid them 10 bucks, और उसके बाद then you give them 1 bill of 1. That fails, for example, if अगर आपके पास 1 का bill नहीं है, तो that's gonna fail. You won't be able to give them 11. DP works, if there is a solution, DP will always work. And the way it works is that it says that I'm gonna try all possible coins or bills and try to figure out which one gives me the minimum number of bills that are required for that amount. Okay, so for example, ये वाला जो table है, you can almost always make a table for the DP solution. It's either a 1-dimensional, 2-dimensional, 3-dimensional table, but it's stable. Okay, so in this case, so you start with the smallest problem. Let's say that you want to give away 0. 0 के लिए you don't need any coins, so 0 के लिए DP solution is 0. 1 के लिए your solution is going to be 1 because there is a $1 bill that you can give them. 2 के लिए the minimum number of coins is 1. You can give them a $2 coin, and so on. But the way we are constructing these solution is this equation at the top. So what we are going to do is for each n, we are going to find out what's the minimum, which coin would give me the minimum number of coins that are required. Okay, so for example, if I am at 11, what I'm going to do is I'm going to try at 11, I'm going to try 1, 2, and 5. So 11 ke upar I will try a solution of 11 minus 1, which is 10. So I would say that I want to figure out how many coins are required if I use one coin or 1 bill, and then solve the remaining problem, min coin of 10. एक मेरे पास ये solution है possible 11 के लिए. दूसरा possible solution is 11 minus 2. So 9. So 1 plus main coin 9. And the third possible solution is 11 minus 5, which is 6, I guess. So it's 1 plus the main coin 6 solution. Okay, so I'll compute all 3 of these solutions and return the minimum number of them. अगर मैं बॉटम अप कर रहा हूँ तो मेन C6 मेरे पास ऑलरेडी सॉल्व होगा. मेन 6 is 2. सो यहाँ पे मेरे पास जो नंबर ऑफ कॉइन्स आते हैं थर्ड केस में वो 3 है. मेन 9 मेरे पास 3 है. तो यहाँ पे मेरे पास जो यूज रेड ना, जो मेरे पास नंबर ऑफ कॉइन्स आते हैं दिस इज 4. 10 के लिए 2 है, तो इस केस में मेरे पास 3 आते हैं. Okay, so I'm gonna pick minimum of 3, 4, and 3, and 3 is going to be my result, which is the minimum number of coins or bills I need for 11 for a target which is equal to 11. I hope that makes sense. Let's look at the, so once you have this equation, this recursive relation, this recurrence, writing an algorithm for DP is piece of cake. Super simple. All you have to do is you have to kind of implement this minimum thing in a for loop. Right? Let's see how this looks like. So you set DP of 0 to 0, and then what you do is you implement the recurrence that I showed. Okay, so DP of I is the minimum number of coins that is possible while trying all the coins. Okay, so you try all the coins and then see if did I highlight the correct line? Yeah, you try all the coins. Okay. Cool. यहाँ पे एक check आपको करना पड़ेगा कि you want to make sure that the amount that you're trying to pay is at least the amount of the coin. Okay, so if your amount is 4, then you should not use the $5 bill. All right. I hope that makes sense. Any questions anywhere?
प्रोफेसर स्लैक पे किसी ने पूछा था एक सवाल कि फॉर 10 आल्सो शुड इट बी 1 प्लस मिनिमम ऑफ 9 एंड देन 2 प्लस minimum of 8 and then 5 plus minimum of 5 shouldn't it be 3 as well? So
100%.
I
100%. That's it.
yeah.
That's the way we do it. So what you are suggesting is a top down approach. You're saying that we compute minimum coin of 11 by computing minimum coin of 10, minimum coin of 9, and minimum coin of 5, right? That's the top down approach. So जहाँ पे जो implement हुआ हुआ है, this is the bottom up approach, which is that you start with 0 and then you say that 0 का solution 1 है, और 1 का solution I'm gonna try to figure out recursively, which is that I'm gonna figure out which coins I can subtract from 1 and still get a non-negative quantity. So there's only one coin which I can subtract from 1 and still get non-negative activity, non-negative quantity, which is 0. So which means कि 1 के लिए मेरा solution 1 है, you figure out solution for 2. So by the time you reach 11, you have already computed solution for 10, 9, and 5. So that's the kind of bottom-up approach जो यहाँ पे implement हुई है. What you are suggesting is equally correct way to do it and equally efficient. It's going to give you the same time complexity. I hope that solves that addresses the question. Any other questions?
Hello.
Yeah. Yep, someone said hello. Okay, hello back. Cool. So this was coin change algorithm, and guess
So I
what?
have
What's
a
the time?
question.
Someone has a question.
Yes, is dynamic programming somehow related to amortized analysis? Because I think इस तरह से लगता है कि the cost is being amortized when the input size is growing. Is it somehow related, or are they some different things?
Aman, no, they are different things. No, so what यहाँ पे जो हम analysis कर रहे हैं, which is the worst case analysis, not amortized analysis. It's possible कि उसके design में कहीं पे कुछ problems आपके पास आ जाएं जिसके अंदर उसका जो DP बनाए उसका I'm trying to think of an example where amortized analysis and dynamic programming coincide. No, man, can't think of any. I mean, I can't rule it out. You can definitely have some, but मेरे ज़हन में नहीं आ रही अभी. So अभी जो हम analysis कर रहे हैं, it's a worst case analysis. Okay, so what do you think is the time complexity of this algorithm for coin change? So you just have two loops. One is for n, then there is inside loop, which is the number of coins that you have. So the time complexity is going to be, maybe I have it on the next slide, n times c. Yeah, n times c or n times k, where k is the number of coins. Okay. And this, so अब DP के लिए जैसे someone observed that there is a space cost, so it's a good idea to mention the space complexity as well. So इस case में space complexity is basically the size of your memo. It will become interesting when your memo is running out of battery on my laptop. When your memo is multi-dimensional. Okay, so we'll see a few examples of that. So इस case में time complexity is linear as well. So you just keep an array of solutions for each value of n from 0 to n. All right,
Professor, I have a
next is
question.
yeah.
In
Go
the
ahead.
previous slide, after the if statement, can you explain this line dp of I is storing the minimum of dp of I comma dp of I minus c plus 1?
Right. This is the heart of the dynamic programming. It's the recurrence that we are implementing. Did you understand the recurrence we saw on the last slide? This one?
Yes. Yes.
Okay. So we are actually implementing exactly this statement. So we are storing this minimum, a min coin n minus c, one at a time in a loop. So we compute it for the first coin and we stored it if it's smaller than the current DP of I. we start with the dp of I equals to infinity, which means that the first time we do change, whatever value comes to हमारे पास dp में store हो जाएगी. The next time we find out dp of I for some other coin, we're going to compare it with the current value. So जैसे for example इसके लिए कहाँ है वो वाला example? यहाँ पे हाँ. So जैसे हम 11 के लिए कर रहे थे, the first time we did it, we found that dpfi would be set to 3. The next time the dpfi for the next coin, which is 2, right? So there are 3 possible coins. तो 3 different values को हम compare करेंगे और उसका minimum हमने store करना है. First time this will be equal to 3. Next time we will get a value of 4. We'll compare it to the current value, which is 3, and we'll keep it 3. We won't update it with 4. And the last time we'll see 3, which is already equal to the value we currently have. So we won't update it next time either. So we are just finding out the minimum value of a solution. So dp of I should contain the minimum number of coins needed to make amount I, and we do it iteratively for all values of for all possible coins that we have. Okay. All right. Let's see. One more example. Here's an example which is based on strings. So you're given 2 strings, x and y, and you want to find out the longest common subsequence that appears in both. So sequence means कि वो order के अंदर है. You want the letters in the same order in both x and y, but they don't need to be contiguous. So for example, you see 2 strings x and y. X is a, g, g, t, a, b. Somewhat loosely inspired by the DNA codes. Adenine, guanine, but उसके बाद B आ गया. Y is G, X, T, X, A, Y, B. Their longest common subsequence is G, T, A, B. Okay, so let me just point them out where they are. Okay, it's the smallest. Okay, so यहाँ पे तो this is where G, T, A, B is. यहाँ पे you start with this. So you want the letters in the same order, but they don't need to be contiguous. Okay, so that's the longest common subsequence, and you want the longest possible such subsequence. And right, so think of the brute force way to do this. So you start with the first letter of both strings, x and y. So in x you see a, in y you see g. There are 2 possibilities. एक तो पहले आपने देख लिया कि ये दोनों मैच नहीं करते, which means के longest common subsequence में ये दोनों letters या इन दोनों में से कोई एक letter है जो नहीं होगा, right? Which means that there are 2 possibilities for you. One, that you move away from A, you discard ke A is not going to be in my longest common subsequence, or you decide ke G is not going to be in my longest common subsequence. Okay, these are the 2 possible things that can happen. And in the worst case, you have to cater for both. You have to try both. You would so what I'm saying is that you should try when you say that A is not equal to G, there are 2 possibilities, that you create an x prime which is equal to G, G, T, A, B. So you move to your pointer away from A, or you have y dash. This is the second possibility, which is that you move forward in y, x, T, X, A, Y, B. Okay, so the 2 possibilities is that you find out the longest common subsequence in x bar and y, or x and y bar. And so now your problem is smaller in size because you have removed 1 character from either string. So you get 2 problems, but both of these problems are smaller in size. You solve them, and then that's going to be your solution, right? Up यहाँ पे if the first letter of X matches the second letter of Y, your subproblem is going to be that you match those two letters and then you move away in both directions. Okay, so you would have X bar and Y bar solution. What do I want to say? Okay, so I want to say that solution of X comma Y is equal to maximum of solution of Y comma X bar comma solution of X comma Y bar. Okay, so this would be the case when X and Y का जो first letter है that does not match. If it matches, then solution of X, Y is equal to 1 because they matched, right? We found a character where they match, plus the solution of X bar, Y bar, where X bar and Y bar is just one letter ahead from X and Y, right? So these are three possible things that can happen. And if you do it recursively the way I described it, you're going to end up with a lot of subproblems which are being solved again and again, which means that there is a potential to apply dynamic programming here, and that's what we're going to do. I hope the problem is clear. Is the problem clear? Okay, I assume that it is. So here's an optimal substructure. जो मैंने ख्याल में अभी आपको बताया है कि LCS of I, J is so LCS of I, J is the longest common subsequence in strings X and Y starting from I onwards. Okay, so LCS of I, J is 1 plus LCS of I minus 1, J minus 1 if they match. And if they don't match, then it's one of the two things. Either it's I minus 1, J, or it's LCS of I, J minus 1. And we are going to store the solution somewhere in the memo, and we're going to return whatever is the best solution whenever we need, for example, IJ. And the DP table, iski jo table banega. Do I have the table? I have an example. Okay, we'll see the example. All right, so you start with the smallest possible problem. Smallest possible subproblem is going to be when X is empty and Y is empty. If both strings are empty, then there is no common subsequence, which means that the length of the common subsequence for empty strings is 0. Can anyone point out what's going to be the length of common subsequence for the first row? So the first row represents that your X is empty, but Y contains first cell में empty, second cell में it only contains P, third cell में it contains, did I do it the PD or DC? So it only contains P. Second cell mate contains B and D. Third cell mate contains B, D, and C. Fourth cell mate contains B, D, C, A, and B. What's going to be longest common subsequence? Anyone quickly? If one of the strings is empty? No?
An empty string.
Yeah, empty string. There's no, the length of the common subsequence is going to be 0, right? If one of the strings is empty, right? So that's 0. So you'll get 0 in the first row, and you'll also get 0 in the first column because it represents the second string is empty, right? If the second string is empty, you don't care what's in the first string. All right. So now we have to figure out if the first string contains A and the second string contains B, what's the longest common subsequence? So it's 0. You probably know that it's 0, but it's 0 in DP case because it's the maximum of two cells. It's the maximum of these two cells. Okay. Remember, when I have that I and J don't match, I have to pick the max of I j minus 1 and j I minus 1. So I j minus 1 is the ith column and j minus 1th row, and j my I sorry a minus 1 j I minus 1 j is the I minus 1th column and jth row. Okay, so इस case में we are picking the maximum of the maximum of the top cell in the left cell. Okay, so that's gonna be 0. A D के case में is also gonna be 0. 0. यहाँ पे we match, right? यहाँ पे when you match, what you do is your solution is going to be, I'm gonna write it down here. It's gonna be 1 plus what you get in the diagonal cell. So I minus 1, j minus 1. Does this make sense? और यहाँ पे कुछ questions हैं लोगों के? Are you good?
Professor, I think
Yes.
एक और दफा explain कर दें.
Okay, let me fill up this table और उसके बाद I'm gonna ask the same question again and probably go through the whole thing again. Okay, so इस case में your solution is gonna be 1. What's gonna be solution in this case? Can anyone just shout out? So remember, if they don't match, yeah, go ahead. Yeah, it's 1. Yeah, absolutely, absolutely. It's 1 because it's the maxima of the left cell and the top cell. Okay, so you get 1. B match हो रहा है, so it's gonna be 1 plus the diagonal, which is 0. So you get 1. BD के साथ match नहीं हो रहा, you get max of the two sides. 1, 1, 1. यहाँ पे anyone shout out what's gonna be here? Yes. Okay, so it's gonna be 2, right? Because it's gonna B and B match, and you look at the diagonal. Okay, so it's gonna be 1 plus 1, which is 2. All right. Try to fill up the remaining row in your head, and ask me a question if what you see on the next screen is wrong. Okay, so this is going to be 1. This is going to be 1. This is going to be 2, right? Max of the 1 and 2. And this is going to be 2. And this is going to be 3. It's 1 plus. Cool. Well, at least I understand what's going on, right? Okay. So any questions? Any questions? Hello? Okay, I think we did cover a decent amount of examples today. We'll see a lot more examples standard programming की हमने अभी देखनी है. I'm gonna share slides up till this point. Go through them. Try to do longest common subsequence with some other example on your own, just to get hang of the recurrence. The main thing about the dynamic programming is the recurrence. You figure out what do I want to recurse on and what the recurrence is going to look like. Once you have that, उसके बाद writing an algorithm is piece of cake, as I said. Okay. Still a chance if you have any questions.
Just a quick question. How would we use this approach to store the longest subsequence? Because we're only storing the counts over here.
Absolutely, absolutely. Very, very good question. So this table shows you that you can find out the size or the length of the longest common subsequence. But how do you actually find out the longest common subsequence? So the way you do it, you backtrack your steps. For example, when you were at 3, what you did was you go diagonal. When you go diagonal, that means that you matched a cell. Okay, so which means that longest common subsequence contains whatever letter you matched here. Okay, इसका मतलब है कि you picked 3 and then you were here. When you were here, you picked the max of the 2, which means that you came from here. Which means that from 2 you have to you can do 2 things. Well, actually, there's only one thing you can do, right? You can just 2 is 1 plus 1, which means that you matched here. If you matched here, which means that your C is one of the letters that you matched, and you came from here. At this point, you came from here. You did not match anything. Or यहाँ पे you came from the diagonal, which means that you matched something here. And this is 0, and 0 came from 0. Okay, so when you go to either left or top, the letters are not matched. You match the letter only when you go diagonal. Those are the letters that are part of the longest common subsequence, and then you just have to backtrack to find out those letters in your table. Make sense?
Yeah, thanks.
Awesome, guys. I think that's it. I'll see you on Monday. We'll have to figure out something regarding the worksheet. We're still working on it. Probably इसको offline करना पड़ेगा. There's no point doing it in Teams. Send me any questions if you have on Slack. I'll see you on Monday. Thanks.